before 3 p.m. break, we may take a group photo outside, so just let everybody know. Hope everybody can participate. And another very, very distinct feature of bridge rehabilitation is that when we build a new bridge, or design a new bridge, we just design bridge as a whole. And that is much easier, simple. But in reality, that once you have bridge in service, and if you want to widen it, or if you want to replace it, like even if you just replace simply the decks, sometimes it is difficult to shut the bridge down. Like if it's in certain area, like an urban area, sometimes you can have a detour, let people to drive in nearby bridges. But in a lot of major highways, and that's only bridge for that whole road, so it is not practical. In that case, you may have to have a staged construction, which requires maintenance of traffic. For staged construction, it's something like it's something like we may have to do it. It's not something we want to do it. In other words, if you have any opportunity to avoid staged construction, that's best. Sometimes it may be cheaper for you to build a temporary bridge side by side with existing, and use a temporary bridge to detour the traffic, so you can build a whole bridge deck as one shot. If you cannot avoid that, then probably staged construction is the only approach. And basically, like this is some photos I show. Like if you can build a temporary bridge. Temporary bridge typically is like made of a modular truss. They can span with different span lengths, and so that it can fit. So all you need is just provide a ramp to tie it in, so that you can do the whole construction all at one stage. Detour is another alternative, as I said. If you have another bridge not too far away, you may guide people to using that bridge as an alternative. Like another thing that when you design bridge, you have to make sure that you should consider how you replace bridge deck in the future. That's why sometimes if you have a bridge relatively narrow and you say, I only really need 3 girders, and ideally you may want to have at least 4 girders, so at least we can have staged construction for stages. If you have only 3 girders, that will be extremely difficult to do. This is an overall view of a staged construction. And if somebody is new to bridge rehabilitation design, he or she may not know that when we do staged construction, we need to have basically a separation, like a physical separation between the construction zone and the traffic zone. And typically, the traffic zone arrangement is done by transportation engineer. So they may say, okay, we need that. We need to keep 1 lane or 2 lanes during construction. Ideally, you should keep 2 lanes, so people can travel in that direction. If you only keep 1 lane, then probably you need a person to control traffic. And that's only for very, very rural area where you don't have much traffic. With heavy traffic area, that may not be practical, so we at least to keep 2 lanes. Another thing that for roadway, you just put the concrete barriers there, but at the bridge, these barriers have to be bolted to the deck. Otherwise, when a vehicle hit, the whole thing may fall off. And because of that, it also affects the quality. Like you can bolt into existing deck, and once you build a new deck, you also have to bolt the barrier into new deck. So you have many, many holes in your new deck. And design consideration, basically, that's all most important for engineers. And when you have a staged construction, in other words, you effectively have to cut the deck. Where to cut deck usually is in consultation with bridge engineers, but the major decision is typically made by transportation engineer. The transportation engineer said, well, no, I need to keep 2 lanes, and each lane has to be that wide, so you can only cut here, you cannot cut there. And then once you decide to cut the deck, the designer has to take consideration that the concrete deck is not usually designed as cantilever. So depending where you cut, if you cut has a big cantilever portion, your deck may not be able to carry the load for that cantilever component. That's very visual. So most of the engineers will know to make sure that to check that part. The real thing, like a lot of people may forgot to check it that, like originally you have multiple girders, and when the truck comes here, so there's a lot of girders will share the load. And if you cut the deck, when the truck comes there, the other girders will not be able to share any load. So you have much larger load, live load on your originally interior girder now become exterior girder. So really depending on how much overhang you have, that may create a situation. So you have to check that part. And this example is just like a staged construction. This is a bridge has a staged construction to maintain 1 lane of traffic and the one sidewalk. So once they cut there, you need to have that. So now you have to check, make sure that cantilever is working. And of course, when you have vehicles here, before it was sheared by many girders, now these will have difference. So that girder may carry a lot more live load than otherwise. So if they don't work, actually in many cases don't work, what you can do is that actually, because there's many such situations, so the state of Maryland developed a standard drawing. This actually is the standard drawing by state of Maryland. So all you need to do is provide a temporary beam which spans from one girder to another girder, and then you just weld a steel stringer. Oh, sorry. So you put a stringer, then you just put like a wedge. Like typically you can either timber or steel. Like timber is fine. You just have like 2 wedges, tie them together every a meter or something. Then you just grout continuously, so that after doing that, this is continuously supported by these stringers. And now this slab is no longer a cantilever. Not only that, when the track load comes here, and all these girders will be sharing the load just like before. So that solved both problems. Another thing you may want to consider is that when we're doing planning of staged construction, we usually draw on the paper. It means it's almost like you look from sky looking down. But in reality, sometimes bridges in space, you can actually overlap in a space. Like sometimes if you don't have enough room, you can alter you can alter the new bridge with different vertical profile. If they have different vertical profile, they may be able to overlap. Once you do the overlap, sometimes if you don't have enough space, it may actually work. And this is a very short introduction of staged construction. If you have not designed these kind of things, and again, the real problem about staged construction is it prolonged duration a lot, and it costs a lot more. And for the designer, when you write a proposal for design a bridge, if it's a staged construction, you should increase your price a lot because a staged construction effectively is a design bridge twice. You have to do a calculation twice and prepare design drawings in many states. But the worst thing is that it does not produce very good quality of concrete deck. Like you always have a longitudinal drawing. You always have a lot of anchor holes to fix that temporary barriers. And also because when you cast deck together, while you have vehicles traveling, it has a lot of vibrations that may also damage the fresh concrete a little bit. Any questions on stages construction? Okay, if not, we continue the next section. Seismic retrofit, and the term retrofit and then rehabilitation is very vague, the differences. But typically, rehabilitation, when we talk about rehabilitation, we mean it needs to be designed to enhance the capacity of a structure. If you don't need to enhance the capacity, if it's just a crack is seared, if spalling, you just patch it, we typically call it repair. In other words, if it does not change anything, we call it repair. And retrofit is something between. Retrofit is like the bridge is okay if there's no earthquake, but if there's earthquake, that may not be sufficient. So that's just for particular reason. Because a lot of bridges may be designed for a situation that the earthquake was not considered, and now we have enhanced awareness of earthquake, so that we may have to strengthen. Actually, in the United States, a lot of states had such program after earthquake, and usually these kind of activity faced just die down when they don't see an earthquake. In other words, you spend a lot of money for preparation of something happening. If something doesn't happen, the money is wasted. But on the other hand, if it does happen, then you can save a lot of lives and other things. So that's why the best approach is design earthquake when you do. Basically, earthquake retrofit is relatively simple. There's only a couple, limited scenarios. And basically, what you can do is just look at what happened during the earthquake. Of course, there's policies of what kind of earthquake should be considered, how you set up priorities, that kind of thing. But in general, how you do the technical part is like that. First, you just decide if your bridge is vulnerable, and the vulnerability really depends on if that is in the earthquake activity zone, and how important that structure is. In other words, if it collapses, it will affect the whole operation, especially rescuing operation. In other words, if the bridge collapses, there's no way for the outside help to reach that zone. That will be very damaging. But if that repair only affects very few people, that will be different scenarios. And of course, there's many other issues. That's why they have different procedures to determine if that bridge needs to be retrofitted. Again, everything you do is also depending on the resources. If you don't have resources to back up your demand, then this kind of exercise does not mean much. So assume we decided these are just basically just using different categories and different characters of the bridge and different locations and different importances, and decide how you select these bridges. And probably, again, this kind of selection is mainly for US. I think a different region may have different approaches to select. And here we basically just will be discussing how we strengthen or how we do the technical part. By looking at this picture, you will have very good sense of how the bridge is damaged during earthquake. Bridge can be damaged by, like for example, that span simply lost the support. And the reason bridge can lose support is very easy. During the earthquake, the superstructure move and substructure move. They may not be in concert, they may move in a different direction. So if substructure moves like superstructure that way, substructure that way, they may lose support, so may fall off. That's why for the new design, we specify the minimum like a support length, so that just make sure the support length is a function of how tall your support is. The taller you have more movement of substructures, and how long the span is, and so and how active the bridge is. So that's one failure mode. Second failure mode is look at these columns. We know that concrete is very good material for compression. So if you only design the structure to resist a gravity load, like if live load, dead load, whatever, you don't need really a big column. Very small column will be sufficient to carry this load. And but if you have lateral load typically people will at least design for like we call longitudinal force. Like in other words, when the truck comes, they have suddenly the brake, there will be initial force, we push the deck, and so or the wind load. But these are usually not very large. This type of load, and so only when earthquake comes like it shakes because the superstructure has big mass, and when that superstructure moves, it introduces an initial force so that it may shear off the column if the column is so small, because they were not designed for lateral load, shear load. That's another mode. Third mode is look at that pier. That pier is treated, and again, similar situation. Like if you design a foundation, like for piles or spray footing, if you only for vertical load, you don't need many piles. But if you have vertical load plus a earthquake lateral load, then you need a lot more piles. That's why if you were not designed for earthquake load, the foundation may fail. So these are the three basic failure modes. And of course, to address the problem, basically you only need to address these three problems. So basically just a loss support. And to address losing support, when you do the new design, you can calculate how much support length needs to be. But for existing structure, you cannot do that. So what you can do is provide a cable or bus restraints. Typically, people use cables. You can use bar, but cable is more flexible. So what it does that if there's no earthquake, it will not be active because it's loose. So the superstructure is free to move due to temperature changes. And then whenever there's big earthquake, so that it's moved beyond its limit, then the cable or restrainers will hold it so to prevent the superstructure from falling off. So that's a relatively simple solution for that problem. And like sometimes like the movement is too large. You may just have like a bearing, like a rock type of bearing. This is like a very old type of bearing people no longer use. But these rockers has a limited movement limitation. Like once it's like it's more than 30 degrees, it becomes unstable. So that may collapse. Again, if you have these kind of bearings, you may have to have constraints, or you may simply replace the bearings. And if you have sufficient support length, then you only need to replace bearings. And if you don't have this, and you can just provide cables to tie it down to prevent it moving. But these are like typically, a lot of people move that. Basically, all you need to do is build like a seat, so that for the concrete seat there, and put another small bearings here. That's a losing support. A second scenario is column shear off. Like column shear off, of course, then it means the column is too slender. If you do some calculation, say, okay, my column is too slender, column resists that shear. So typically what you can do is you make this column bigger, in other words, build another reinforced concrete over it. Or sometimes it's not necessary, so that you may simply provide a jacket. Jacket, originally you basically just provide two pieces of steel plate. You have that steel plate, you put together, and there's a little bit of space. You grow the space in, and you weld the two vertical lines. You provide confinement. Once you provide confinement, the steel tube itself is a shear reinforcement, so that will be able to carry sufficient shear. And now, because FRP has become cheaper and simpler, so typically people are using like a FRP to wrap them up to provide shear reinforcement. And that also provides confinement to increase ductility and to reduce earthquake load. So, and sometimes it's the failures, we call shear failure, but it's not the pure shear, because you still have vertical load. So lack of confinement also contributes to the failure. So as I said, the failure is really very complex, but the problem is the same. You don't have enough confinement or shear reinforcement. It's the same thing. Or you don't have enough section size to resist shear. So that's caused a problem. So that's why in the earthquake zone, we try to provide a lot of spirals, just to provide as much as confinement as possible, so that this kind of failure will be less likely to happen. For two reasons. One is once you have more shear reinforcement, it has much larger shear capacity, and also have better confinement. In other words, it will resist more load. And also research found that if you have confinement, actually the shear capacity of concrete also enhances. The shear of concrete is effectively the tension in the concrete. If you rotate the axis of the stress, it's become a tension. Sometimes you don't have enough overlap for between footing and column, so that may be a problem. So, and that's why, if in the earthquake zone, your lap length should be longer than your static lap. So sometimes that may happen. That happen usually is a contribution of too short the lap spreads and too little confinement. Both were acting as same function. So these are if the column is too small for shear, so they provide steel jacking, which is a weld, and they grow the space. And of course, FRP jack jacketing or sheeting is much easier to apply. When you apply FIP, I don't know, I forgot to mention, it's circular is okay. Like if you have rectangular, if you don't have, if you have very sharp angle, like sharp edge, typically you want to smooth it up. And otherwise, if it's very sharp, because it's almost like the final product is almost like a glass. It's very, very hard, so it may hurt people easily. And also, people may hurt the material easily. It's very brittle. And actually, people always ask me like, how do you decide if a bridge is pretty or not? Of course, there's a million different answers. To me, my answer typically is I don't really care about the shape or the color particularly. To me, if you look at a bridge, if it's just a structurally reasonable, structurally efficient, it look to me very nice. If it looks strange to me, in other words, not structurally efficient, may not, then I don't like that. Like for example, when I look at that bridge, look like the pier column is too slender to me. Of course, if you do a retrofit like earthquake analysis, you may find that is just too small. So sometimes, once it's too small, you put a steel jack or wrap up, may not increase sufficient capacity. In that case, you may actually make it larger. Like in this case, actually they make the column much larger. They basically just put another layer of reinforced concrete. And to resist transverse earthquake, because earthquake can be longitudinal direction, transverse direction, or can be in any directions. So provide shear key is very essential. I use shear key a lot for new construction, new designs as well. So, and also if you have a very slender column, one way to achieve that is just build a wall between the cylinder columns so that just become a solid pier. Another failure, as I said, the third failure is foundation failure. Foundation failure is typically the pile failure, but it can pile failure when you have too much load, either bending or compression. I mean, either tension or compression. Typically, it's compression. It's just a crash, and sometimes it could be the pile cap fails, either shear failure or bending failure. But most failure is caused by the pile itself. And of course, there's also possibility of a failure of these. But failure of these typically is overlap. We just had a picture, and they just don't have enough lap reinforcement so that they're separated. So to do that, typically we provide micropiles. We add additional micropiles and build a monolithic concrete new pile cap, so that you build a much larger footing for the piers. Sometimes you may not need big piling. For example, for that bridge, it has the pier is too small, and that will be okay if you don't have earthquake. When for the vertical load is okay, but when the earthquake comes, then you will say, okay, I don't really need the new piles. All I need is tension anchors. You could have a new piles, or you can actually install a soil nail or kind of a tension anchors, so that when the earthquake comes, these tension members can resist load as well. That can be considered. Sometimes it's cheaper to have tension members than compression members, so that you don't have to have equipment to drive piles down. Another thing to pay attention, the heavily skewed bridges. Sometimes this is caused by design errors. Even if some bridge was designed recently and they consider earthquake already, the other ones were designed old, very, very early stages. They did not even consider earthquake, so you have to do retrofit. And for new ones, sometimes a lot of people use design skewed bridge. They just treat that as a regular bridge. But the problem is, skewed bridge don't have it's not symmetrical. When the earthquake load comes, they tend to rotate. So once they rotate, they create additional a stress at edges. So that for example, when that earthquake comes, that try to bend transversely, and that against transverse cause that girder to crash, because the girder was not designed in that direction at all. That cannot resist much load. So that's something you have to consider. So to do that, typically you may have to design different things. Another is that instead of using cable constraints, you may make the girders linked, but if you don't want to, so you can put a kind of a bolt connections. That is not moment connection. Basically, just make them move together, or you can have cables, provide cables to tie down into the pier, or this is tied down to the abutment. Actually, these are the promotional material which was produced by California Transportation Department after a big earthquake, and actually that's almost more than 20 years old. So at that time, actually, they produced a material to let public know that the transportation department is doing something. So in these, it basically just summarize all the things they were doing, provide cable constraints and enlarge footings, and provide steel casting to enhance the shear capacities. And for the future, they will provide more spirals to prevent that kind of failures. And so basically, if you look at these pictures, you will know everything earthquake retrofit is required. And basically, a strategy is basically just ensure superstructure can withstand the horizontal movement, so that the deck will not collapse in the first mode. Second, so these is simple, so that you should spend most money, money to solve all these problems. Once these problems solved, you have money left. It addresses the single column issue. Single column usually is very vulnerable. You might either jack it and add more load, and then it's just the multi-column. Multi-column is typically more stable. So it just address that first, then address these, and then address that. Most organizations address these. It doesn't cost much money, and they try to address these as much as they can. For these ones, probably just leave it alone. So actually, for the new design, design rehabilitation, actually, when we talk about rehabilitation, we always have to think about new design. That's why it's very important for the bridge engineer to get involved into bridge rehabilitation. Once you have done rehab project, you know what problems are, and you can improve your new design accordingly. For example, if you find the drainage issues, and then you may say, okay, maybe we should try to eliminate deck drainage as much as we can. We don't need for that many. We can do a more detailed calculation. So once you have less drainage, you have less things to maintain. And the same thing, like when you do a rehab, you always have problem with expansion joints. And during the new design bridge, you say, why do I need expansion joints? Can I just make them continuous? Even at the abutment, now a lot of people use an integral abutment to have integral abutment with superstructure, so you don't need any expansion joints. So the same thing, once you've done rehab, and when you go back to the new design, you would know that like the best approach is build a structure very, very ductile, and then just design an essential bridge with elastic superstructure. That's an option too. Like if you cannot do these one, you just make sure that your structure is so strong. Like these are typical small bridges. And assume everything elastic, and assume every member is very, very strong. So I don't care about earthquake load because it's too big. But if the bridge is very, very large, you want to design everything elastic, it becomes impossible. And so that in that case, typically what you can do is you introduce a plastic hinge. And like for example, if we have a bridge superstructure, and that's on top. If I simplify, if I have only one fixed pier, I have a superstructure. And actually, I mentioned yesterday briefly. So when the earthquake comes, then there will be a force movement because the superstructure has movement. Movement creates the initial load, and so that is a function of the mass of my superstructure, and also a function of my acceleration. And but no matter what, if I have, for example, if I have a hinge here, so no matter how big the load, there's no load transfer to my footing at all. But in reality, that you cannot have hinge because the whole structure is not stable because of mechanism. So what you do is that I make that link very weak here. So then I have a bending moment capacity here, at here. So once I know the bending moment capacity, then that bending will not be larger than my capacity, so that then I will know what the maximum earthquake load will be. Then I can design accordingly. But then you have to make sure that when you have these assumptions, that the bridge foundation and your column will have to have sufficient ductility, so that otherwise if you move a little bit, the crash, then it will not work. So like the philosophy of design that during very, very big earthquake, your essential bridge should still be open to public. In other words, emergency vehicles should be able to pass the bridge with very, very minor repairs. And so just that, because of that, you have to make sure that you have like very, very sufficient ductilities. And if you have really big bridges, you may introduce a fuse mechanism. In other words, and the earthquake load were not exceeding my design value. Once it's exceeding design value, which is a very, very extremely condition, then that fuse will break, so that you will not be able to exceed that capacity. And so that is a more controlled way than normal like a plastic hinge. Normal plastic hinge is something that you can estimate, but this is more manufactured. But like for structure and earthquake analysis is a relatively straightforward, and it's a function of location. Location means the earthquake zone. This different location has different earthquake acceleration and duration and so on. And basically just try to produce a ductile condition so that you can develop a plastic hinge. And ductile superstructure is not usually allowed. You should not introduce something that say, okay, my superstructure is ductile. You always have to assume your superstructure is one piece and a solid piece to move around. And actually, the next slide will show you typically what model you should use. Again, during the earthquake, for your plastic hinge design, you have to assume, especially during earthquake, you have to consider P delta effect. In other words, once you have deformation, you have P that will increase your bending moment. Typically, you can have this kind of model. So these were called plastic hinge. There's a plastic hinge. Sometimes you can also develop plastic hinge on top, and it's even for a skewed bridge, it will be similar situation. You can have this type of basically this type of structure model is allowed, and this is not typically allowed. You have fixed at bottom and has plastic hinge near the top, and these is allowed provided you have special permission. In other words, this is usually for large bridges. You have dampers for the superstructure and you have plastic hinges each way. This is the same concept design for Auckland Bay Bridge. Auckland Bay has only one pier and a very large superstructure. So, and they use dampers on the superstructure. And this is not a good idea. If you have simply supported structure, then you have to make sure that if you have simply supported structure, you have to make sure that you know plastic hinge. In other words, your pier has to be very, very solid. If you have simply supported and then plastic hinge, it has such a big movement, then everything will be fall apart. Yeah. Any questions? Retrofit itself is relatively simple. They only address these three things, and most organizations don't do that much anymore. So, and the retrofit is to gain knowledge of what may happen if you don't do something during the new design. That's why to address the problem, we should start from design phase. And no question? So, how sensitive, actually, I haven't looked. How sensitive is an earthquake here? Is it really? When was the last major earthquake here? People don't remember. Okay. I mean, just 6 years ago? Yeah. Okay, and it, major damages?
Nearby the source of the earthquake, more or less. Yeah, but we had an earthquake in 1991, and the damage was a lot of bridges because of the deflection problems. So we had some problems with bridges in the past.
Yeah. Yeah. Basically, a bridge earthquake vulnerability at the beginning, I didn't show too much, is to determine how vulnerable and how urgent this needs to be addressed. But in reality, that if you don't touch that bridge, you don't really have funding to address just simply for earthquake. So that when you do a rehabilitation of a particular bridge, at that time, we take consideration of if that bridge is vulnerable to earthquake. For example, if we are doing deck replacement, we should take a quick calculation to see what happens for footing. If earthquake comes, will the footing be able to resist additional bending? And if not, you may say, okay, we need to put a couple of new piles and make that footing bigger so that it can resist earthquake. So in other words, earthquake retrofit usually is a part of a rehabilitation project. It's very, very difficult to be a standalone project. Being standalone project usually is after earthquake, a couple of bridges damaged, then you may say, let's look at all other bridges. So next earthquake it won't damage. At that time, you may have momentum or the possibility of funding for that. And if nothing happened, and all of a sudden people say, let's look at the bridge to see what happened to earthquake, that will be difficult to achieve. Oh, yeah, sure.
I would like to know, for example, you are from the government, no? You work in the government.
Yeah.
So, if we apply the standard norm, if you check the structure that was designed with that norm, you as a government, if you apply now the new norm, the ASTRO, you will see that one of that pier, for example, it doesn't how can I say this? They are failing the norm. If you apply the new norm for that structure, so you have to retrofit this. So
yeah.
You as a specialist, you are doing that as a consultant or not, something like that. For example, if you know that the bridge from 1951 was designed by F.ASCE, the standard norm, but if you apply this moment the actual norm, you will see that bridge, the substructure, or it's not in the range, so you have to rehab that bridge.
Mm.
So I would like to know if you are, as a consultant, as a government, you do that or not.
Yeah, if you have funding, by all means, you can do that, because like many things, just like buildings, like before, like old buildings, actually I don't know if here, they might not have fire protection system, and later the government changed the mind and say, okay, all these auditorium, you need to have fire sprinklers in case there's fire, they can have sprinklers come down. And that usually is requirement for new buildings. And of course, government has already said, okay, for all the buildings, you have to do the same thing. Then everybody has to do. It's just basically the policy issues. And the government may say, okay, and you only need to do that for the new buildings. It's the same thing for the bridge. Once they change the design code, or the design code change itself, you may say, okay, let's apply this code for all the bridges, which is very unlikely. The reason is that all of a sudden you need to spend a lot of money on it. So typically, they may say, okay, that does not apply to the old bridges. But again, that will be a government choice. The government may say, but if you have to repair these bridges, you may take consideration to bring every aspect into the new code requirement. Or they may say, never mind, this new code does not apply to old bridges, period. So it's a policy issue. But as an engineer, regardless, engineer, typically you cannot initiate the project. Like for example, you cannot say, you are not policymakers, so you cannot say, let's do retrofit for all the bridges. They may say, who gave you that authority, where the money is. So, but you have authority to say, once you do a rehabilitation for this bridge, you say, oh, well, I need to reinforce that column because that column is too slender. When earthquake comes, it's not, because the high-level government officials don't even know what you are doing. But all you do is just make that bridge safer because you are working on this bridge. You may have another bridge which has the exact same situation because you are not doing another bridge. You may not be able to reinforce that column until you work on another bridge. But that's a normal procedure. But like in US, there's a priority, which I said. Priority, if we follow that, will be different approach. The priority say that to see how vulnerable these bridges are and try to prioritize your funding to fix these things. And that's just on paper, but in reality, that did not happen because nobody has money to do things. Just like if you have only money for putting off the fires, that fire is there, there's fire there. You don't have anything else spent to do something which is not on fire. Just keep on going, which is typical in California. California has a lot of wildfires. It's not like here, California is very dry. So every year they have forest fires a lot. So everybody said, you need to spend money to cut off these small bushes and trim them. If we all forest has big trees without small bushes, it will not catch fires. They say, yeah, we need to do that. But now we have that many fires. I need to spend money on fires. I don't have money to cut these. So, that's the same situation. It's whether you should do it or not is different than whether you have resources of doing it. Yeah, another thing is the decision models. Decision models is actually a very, very new concept. People make decisions, people make decisions every day, and not for example, you make decisions where to eat lunch and how you go home and whether to attend this seminar, that kind of thing. There are many decisions. People make decisions based on that instinct. In other words, they don't have really do any calculations or something like that. That's why traditionally, decision making is an art. And not until 1930s, a couple of professors from the United States, particularly in Princeton, these are basically mathematical professors, and they started studying decision, how people making decisions. And once professors or researchers get involved, all of a sudden they develop models and mathematical equations. And once that happens, it's no longer an art, it becomes a science. That's why we're talking about here now. So, decision is very, very complex. It's not really like science we engineer know or scientists know. For scientists or engineers, we know there's right answer, there's wrong answer, there's nothing in between. For decision making, it's it's a spectrum, like a rainbow. You don't really have very, very distinction of where, but you only have a sense of very much here is very purple colors, a very, very high frequency light, and these are a very, very red or yellowish and a very low frequency light. Actually, again, we're talking about frequency, it's more like science, but that's the kind of feelings. Decision making is the same. There's there's some decisions is yes, right, or wrong. But basically, it's how good your decision is. excellent or good enough or very, very poor decision. Very much just like a categories. Almost like when we do a bridge inspections, it's just like you can use a 1 to 9 in like a scale, or you can use a 1 to 1,000 scale. You have very, very detailed, but that does not give you too much because your theory itself is not that accurate to predict. And that's why it's just it's a science, but it's not like a science as we normally know. But there are certain aspects of decision making is like almost like mathematical, and so that can be very, very precise science. And so actually, again, there are hundreds of decision making process at models, so we cannot possibly teach everyone. Actually, I don't even know most of them. So I only select a couple of ones we typically used by engineers, and either decision making for the projects or sometimes just for everyday life. And these are the ones I select. Basically, the first one is called life cycle cost analysis. Life cycle cost analysis is actually in the civil engineering curriculum. Typically, it's part of construction management. I don't know if you have a construction management class here. Okay, yeah. In that part, you will have to basically make some kind of decisions based on the costs, whether the project is good or not, and the cost. Basically, the life cycle cost analysis says that when you make decisions to choose which project you should proceed or which option you should select, you not only should look at the initial construction cost, you should also look at like the future maintenance cost. And like for example, if you buy car A, car B, you look at like one is Honda Accord, Honda Civic, another is Honda or Nissan Centro, for example, and one have a little bit high price, one has low price, and then one has less maintenance cost, another has more maintenance cost, and another may have resale value, high resale value, another has low resale value. Then what you can make a comparison, which one is better? Of course, most people actually based on decision of which car I like. They look nice, something like that. If you just forget about other factors, just look at the cost alone. And then what you do that, you just put the initial cost, and usually you would have to define the life of your product. For example, for car, typically we said, okay, my life for that project car is 5 years. So I spend initially, first year, I spend that much money, and every year I spend money for maintenance, gasoline, and so on. And at 50 years, I still have a car, so I can sell that car, and that will be money. So we add all the initial costs and the maintenance costs, then subtract your resale value, they make comparison. But that's just too simplified. We all know that the cost of the money now and the money in the future have different values. So that's why if you spend money in the future or if you receive money in the future, you need to discount back to the current value. We call it present value. So only after you convert all the dollar in the future into the current value, then you can make comparison to see which project costs less. In other words, owning that car for 5 years, which one is less expensive. So that's basically the concept. And again, like using examples, like I have a car for $20,000 and car A, and the cost, the maintenance is like $4,500, and assuming inflation is 3%, and the resale value is $5,000 after 5 years, and the car B has a similar data. So which car show you buy, again, you just say, it just calculate all the money you spent, subtract the money you received. So like a car A, initial cost, and the first year you spend how much money. Basically, because you have like a 3% inflation rate, so we assume everything happened at the end of the year. You can assume everything happened at the beginning of the year. But if it's in the middle of the year, it's just difficult. But for comparison, it does not make any difference as long as you assume both are the same. So at the end of the first year, you will have like 3% inflation that, but because you borrow money, the cost of money is 6%. In other words, you borrow money from bank, you assume that, and then you discount back, so that after you discount, it becomes like 4,300, actually less than 4,500. And you do the same thing the second year, that will be actually dollar value you spent, but that's a present value. And that's dollar value spent is like this portion. And then you discount back, and that's actually the present value. And you do the third year, fourth year, and fifth year. These are each year you actually spend money. And the fifth year, you receive 5,000 money for selling your car, and you discount back 5 years, which discount rate is usually the cost of money you have. You borrow money or whatever the interest rate may be. And then so finally, how much money you spend is the initial cost plus 5 years maintenance, subtract that by the salvage value, and then finally it got 36,900 and so on. In other words, if the car dealership say, well, you give me $50,000, I give you free gas, free maintenance for 5 years, and where you do that, actually, you say, no, I don't want. Actually, the real cost is only that much for a 5-year project. And you should do the same thing for car B. You do the same thing for the car B, the total cost is that much. Then you basically just compare which one is cheaper for you so that you will choose. So that means car B costs a little bit less. So although car B had initial price is higher, but still good value. Also, like for a second question, second example is like if an office building costs like $50 million to buy, and the rental is estimated to be like $3.5 million a year. That will including all the allowance for vacancy, that kind of thing. And the operation cost is $1.2 million a year. And assume like the inflation rate is 3%. And after 20 years, you can sell that for $100 million. And the cost of capital, which is the mortgage, is 8%. Which can be mortgage or can be expectation of earning. Like if you don't need to have mortgage, like how much money you need to earn to justify this project. That will be the cost of capital. So you do the same thing, just like all the money in is positive, all the money out is negative, to see if we add together, if it's still negative or positive. If it's positive, then it's good, you make money. If it's negative, you lose money. Basically, that's how you do that. So you basically have like initial cost, which is a negative money out. And then every year you have revenue and expense, and you times the inflation rate. You assume revenue and the expense all linked to the 3% inflation, so that each year you will have these. Then all you do is just add 20 years income plus, after 50 years, you can sell the building for another for another money. So actually, then you can actually calculate these. There's equations you can use and to write. If you add all 20 together, you don't have to do one by one. Actually, there's mathematical equations like for all 20 years all together, it's that equation. So you have the cost, initial cost, and all the income and after 20 years sales, just to see if the net present value is positive or negative. Again, you can do the calculations based on mathematical equations, and finally, you find the cost and all the money in and out is still positive, so that it means you can not only you can make like an 8% return, and actually you can make 1.8 million more. So in other words, if somebody says, no, I don't want to sell for 50 million, I want to sell 51 million, you may still say, okay, I still can make at least 8% return on this. So that's a life cycle cost analysis. I just don't have to give us another examples. So another decision tool is called decision tree. Decision tree is not as popular as life cycle cost analysis. Because life cycle cost analysis actually, when we make like project decisions, we use that quite a lot. Decision tree is like that. If you have like multiple decisions, and you don't know really which decision you should make. In that case, you can just build tree branches. Like I have decision 1, I have put data into decision tree, branch 1, branch 2, branch 3. I just calculate each of these values and to see which value give me the best. And like as engineers, usually we learn things much easier from examples. So I just give you examples how that works. Like for example, if I have 2 projects, one project A costs like 100 and has 50% chance of making 120 and 30% chance of making 180 and 20% chance of making 50, and project B costs 120 and has 50% chance of that basically just all the probabilities of different returns. So which project you should choose? Basically what you do is I build, there are 2 options, so I build 2 branches. I have first branch, I put that basically just like values of like 120, I have 50% of that, and 30% of that, and 20% of that. This should add into 100%. So I use the probability times the value, so I got these. And I got total, I add them together, I got 124. In other words, for the project A, I have most likely I can make 124 out of project A. You may not exactly make that much. That's what we call expected value. What expected value is the probability and times the event when that happens. Like for example, if we buy a lottery, we'll have one out of a million chance of winning lottery. And if you do win the lottery, you win 1 million. So what's your ticket value? The ticket value is the probability, which is 1 out of 1 million, times the value when it happens, which is 1 million. So you times together, it's 1 million. So if people sell you these tickets for $5, you might say, no, I don't want to buy it. It only costs $1. But of course, you cannot buy it for $1 because government says, well, we have to collect money for the charities, and we want to collect money to pay these salaries. So they may sell you for $2. So that's why, in reality, you don't make money. If it's just simply for the sake of making money, if you just think about it for fun, that's okay. It's same thing that that's called basically the fundamental of risk management. Risk management, what says, how do you evaluate risk is the probability of that risk and the consequences of the risk when that happens. So you multiply that together, that will be the value of your risk. So and that's why, and nowadays when we talk about risk management, we have to quantify that, and that's become a science. It's not art anymore. And so the decision tree is like that. And so, and yeah, there's a lot of examples. Like, probably we still have some time. We can do another example. Like, for example, Mr. Brown works for government with an annual salary of $80,000, and he has 5 years to retire. And he got a job offer in a high-tech company for $100,000 a year, which is more than that. But there is 40% chance he will lose his job after 2 years, because the company gave him 2-year guarantee that he will have job at least for 2 years. But if he lost his job, he will have 30% chance of finding another job, which is a low-income, low-paid job, after 6 months of employment. Otherwise, he will never find a job again. And he typically will receive $50,000 if he lost job, because like a government compensation for job losses. So if we ignore everything, like if you just taking consideration of money, so would Mr. Brown take a job, leave government, or he should keep his government job? So which one give him more money? So in this case, it's difficult to make for Mr. Brown to make decisions. What he can do is that he said, well, how many decisions I have to make? Change job, not to change job. So it's easier. There are only two choices. So we just build two tree branches. Like tree branch one, like he will say, okay, let's try what would be value if I change job. Because if he change job, he has a 60% of chance of not losing job in 5 years. After 5 years, he will be retiring no matter what. Then if he does happen, so he has 5 years of $100,000 job, he will make like $500,000. And if he lost job, he has 40% chance of lost job. And what happens if he lost job? He may find another job. If he found another job which is 30%, that is like if he found a job, he will have worked 2 years for a high-tech company. He makes that much money, and he will got $50,000 unemployment compensation, and then he will have another 2.5 years with low income, so he will be able to get $400,000 total if that happens. But if he lost job and he never found a job, he will only get that much plus unemployment, so that he will only get that much. Of course, if he never lost job, he got that much. And if he does not change job, he will get, because he has $80,000 a year, and for 5 years, he will get that much. So how do I see which one is better? Like I know these values. I want to calculate value for these tree branches. So I use that result times probability plus that result times that probability. So I got that tree branch value. And that value times that probability. And this value times that probability, I got that value. So in other words, we call it expected value. In other words, if he changes job, he will expect to get $418,000. But if he does not change job, he got expectation of 400. So that's expected value, but it's not exactly what he can get. He can get more, or he can get less, depending on what situation combinations. But in that case, he should change the job to get more money. But again, this is like a very, very statistical thinking. It's not certain. It's just like a lottery ticket. If you win lottery, you say, well, I want to spend $1, I got $1 million. It's a good deal. Another thing, linear programming. Linear programming actually is very, very popular for engineering and scientists. And not many people may know the terminology, actually. What linear programming is that if you have decision making and you have boundary conditions, you can mathematically calculate what will be the best alternative. In other words, I change my boundary conditions to give me optimal answers. I'll give you an example, would be easy. If I have a wall, this is my piece of wall here, and I give you 100 meters of fence, you can circulate a rectangular shape. One is against wall, you have built 3 sides. I want you to circulate so that you get the maximum area. So you may say, okay, I can have 1 meter here, 1 meter there, and then 98 meters. You can calculate the total area. And you can have 10 meters here, 10 meters there, and 80 meters there. You can have a million or infinite combinations. But then you have only one solution mathematically. So that's called linear programming. In other words, you have a boundary condition. The boundary condition that when I add 3 sides, it has to be 100 meters. That's a boundary condition. And my objective is to maximize the area it can circulate. So my objective. So if you know your objective and if you know your boundary conditions, you can ask computer to do a linear programming so that it will give you best solution. And that usually is the only solution. That's purely mathematical. So you will know that if we have a 25, and 50, that gives me the maximum area. You can have other combinations you can try. Nothing else can give me more area than these. So that typically have one solution. So that's a linear programming. Basically, for most of the asset management, linear programming is always part of it. It's ways to achieve optimize the solutions. Yeah, that's linear programming, and basically we can have an example Mr. Black has 80 acres of farm. He has choice of farm farm pigs or grow corns and wheat, and the net profit for each acre is 500, 250, and 200 per acre. If they do different things. And of course, there's always boundary condition. If there's no boundary condition, obviously he would farm the pig to get more money. But the boundary condition, the regulation limit him has 20 acres of pig. And if he has more than 20 acres of pig, he will have to pay environmental impact fees. And he also has a water right. He has only 25,000 tons of water per year. So but each pig, corn, and wheat will consume different amount of water. So in other words, he has to manage how much water he has to arrange. So in that case, how would Mr. Brown to arrange how many acres of doing what to maximize his profit? So in this case, we know the objective. Objective is to maximize profit. And the boundary condition that basically there's variables. The variable is we can assume X acre of pig, Y X of corn, and 0 X of wheat. And so that the boundary condition will be x plus y plus z equals to the total acreage he has. And the profit will be because each acre will, x will make 500 and y makes 250 and z makes, so that f is the total profit. So all we need to know is that what x, y, and z should I choose so that my f is the largest. So that's called linear programming. So basically there's boundary condition. The boundary condition that the x and y, z add together cannot exceed 50 because he has only 50 acres. And also the total water consumption, like x needs 1,000, y needs 300, and z only needs 200. And if you have these all together, is how much water it will consume. It cannot exceed that. So once you have two boundary conditions, you just put into linear programming. Actually, a lot of software has linear programming, like for the MathSCAD. Actually, this is MathSCAD. MathSCAD linear programming is like you have P, you can maximize f, x, y, z. Then MathSCAD will automatically select x, y, and z to give you maximum P, which is f. I want to maximize the f. I want to know what x and y, z will be. So this will be, MathSCAD will say, okay, you have that much for x, that much for y, that much for z. That will give you a solution. So it will be extremely difficult to do linear programming manually. Typically, the computer can do that. Of course, you can do manually when we did not have computer. You can develop equations, but because once you have x, y, and z, three things, variables, it's extremely difficult. It becomes a curved surface. If you have only x, like for example, the first one we discussed, you only have x, and actually you could have y, but y is equals to 100 minus 2x. So in other words, all you have is x, so that you have x times 100 minus 2x equals to f. So that you have only one x. In that case, you can using derivative. Once you have derivative, it's a single curve because you have only one x. You have single curve, you have derivative, you can find a tangent. And once you have tangent, you will be able to solve that. You can do manually for things like that. Once you get multiple variables, manual calculation is extremely difficult. So what actually, I asked like a math professor, I said, how do people do this, like a MathSCAD? How do they solve equation? He said, well, it's relatively easy. They just try different x, y, z, different x, y, keep on running, and to see which one is better. Because every time they try x, y, z, they got a p, and to see which one gives them the largest p, and that's how they did. So they don't care about the theory. They just try, and say, okay, I found the answer. Okay, once you know the x, y, z, you can substitute that x, y, z into the equation, like a f. You can calculate. So in other words, he will be able to generate $16,000, a little bit more than $16,000 of profit. So no matter how he arranges his farm operation, he cannot exceed more income than that. So I just jump to another one. Actually, marketing people use linear programming quite a lot. Like for example, they want to know how much advertisement they need to spend. If they spend too much advertisement, that money to generate extra revenue may not justify. So that, in other words, not more the better. It's always some kind of conditions. Again, any theory, that's why I say it's not really perfect, is that the calculation can be perfect, but you have to make assumptions. Like all assumptions is man-made. So that's why even the mathematical perfect model will have to be manipulated by the persons. And that is very, very widely used decision tool is called decision matrix. I don't know how many people know decision matrix here? It's not popular. Actually, decision matrix is very, very simple, very, very essential to be used. Like every time when you make decisions, and you have many, many factors to consider. Like which factor is more important, which is less important is, like for example, if we want to interview somebody for a senior bridge engineer, and before you're interviewing people, you have like 3-4 people for interview, how you decide which one is better? You may have some kind of consideration as like what is her education, what is her or his working experience, which university he graduated, and how much salary he or she wants. A couple of factors. They say, okay, let's interview, let's decide. I just rate each people interview, I rate these factors. And of course, not all the factors of same value. Like for example, you may think education is a lot more important than what he or she asks for salary, and I'm willing to pay more if I can get better qualified. And you may say, okay, yeah, education is important, but experience is even more important. So you may give them weight, if I have different factors, I give weight to each factors. And then during the interview, you may look at, and he's talking to him to see what experience he has. So each person, like you have better experience, I give you a 9. And she doesn't have very good experience, I give her 6. And then later, do evaluation of salary, and you want like $60,000, and she only wants like $20,000. So I say, well, the salary expectation, you are so poor, I give you like a 2, and I give her 10. And then the others are rate. And finally, I just add, like I using the rate for each item and the weight of each time. I multiply and add them together just for each person. And I just see which one get the highest overall score. Then I may just offer a job to that person, which is very, very similar for many, many decision makings. Like for example, if you want to select somebody for project, for design projects, for example, you don't rely on the cost alone. You want to look at their experience and what people they propose and so, and their locations, how close and so. You may want to do different factor evaluations. That is very, very typical for bridge selections. Like you don't select a bridge based on price only, different type. You may, sometimes you may see, I really like the bridge, look nice, but how much money you are willing to pay for that? It's a function. In other words, you may have much higher weight for the price of that alternative. You may have a certain weight for the appearance, how beautiful the bridges are, and you may have a weight for if there's environment impact, if there's any local contractor to do the work. Sometimes I'm willing to pay more for this type of construction that local contractor can do instead of other people from America do that. And because when I spend money locally, it's like stimulate local economy, and so you have different factors, different factors may have different weight. So that's why you decide which weight these factors should be, and then make decision based on the final. So that's basically the decision matrix. It's very, very simple. So I'll give you an example. There's three, like a bridge has 3 design alternatives. One is single span, still good. Another 3 span, still good. Another 3 span, precast concrete good. Then I develop, basically they have different cost estimate. And they all, first of all, you have to develop a must list. A must list is that if any of these projects does not meet my must, in other words, that is so essential to me. If you don't meet that requirement, I don't even consider you. So these have to meet, the master list has to be able to meet like hydraulic requirement, have to meet like a loading requirement, have to meet like a transportation, like a design speed requirement. Another one list is that that is important, but these factors I need to make comparison. So it's not simply yes or this is just simply yes or no question, and this is like how I do the evaluation. I of course the cost and the maintenance costs and the constructability, like how easy this can be built, and the construction schedule, how fast they can build, and the environmental impact, and how they look, and how long this structure can last. So if I consider these as factors, then I develop a decision matrix. So I have these as one list, but that's must list. Must list is just click to see if this bridge meets that requirement, yes, and that yes, and that yes. If any of us no, then you just don't even consider that as option. And then you just, the tricky thing is give weight. Like how important is that? It has different people have different opinions. So once you decide like how important is weighted, when I do a weighting, I typically using weight to 100%. In other words, add everything to 100%. Some people use a weight which is not normalized. If you don't normalize the weight, so it's very difficult. Then you just have a 1 to 10 score, or you just score each of the alternative. Like for example, the steel girder, the initial cost, you based on the cost estimate. This is best, it's the cheapest. You have a high score, low score, and the maintenance. You say, okay, that concrete has less maintenance, and then the steel, so you give different scores, and so once you give all these scores for different elements, factors, then just that plus times that plus that times that, you just add all together for each of these. And then these give a high score, so you may say, okay, I choose these because these give me the best values. So that's how I make decision. Okay, so basically that. Another series, basically computer simulation. Computer simulation actually is like I had a Ph.D. series on computer simulation. I did that about 20 years ago. At that time, computer simulation was not popular topic, and now it's become very popular. Everybody knows. Like traditionally, when we do a estimate, like for example, for a civil engineer, the easiest way is to talk about a construction schedule. Like we have a CPM, critical path method. CPM very much you break down the project into activities, and each activity you will have like a logic link, how these activities are related, and after you done that, you just assign the duration of each activities. For example, if I build these rooms, you may say, okay, the activity may include, after the structure is complete, I may need to finish the wall, and need to finish the ceiling. I need to install this lighting, and then I need to finish the flooring. I need to put these seats, and then I need to install these electric communication equipment. You have many activities, so you just assign them the duration, so you estimate how long it will take to finish these rooms. And actually, we know that once you do that, once you have done that, you say, okay, the total duration is 3 months. And everybody knows 3 months is the estimate. It can be like 2.5 months or maybe 5 months. You never know. It's like so. What computer simulation does is that instead of giving the computer how many days per activity, you let computer select. Like for example, to finish this floor. Like if you have done 100 times at different locations, every time you have different day, like sometimes you finish 31 days, sometimes you finish 35 days, sometimes you finish 28 days. You have these data. So instead of telling computer how many days for that duration, you just let computer select. So you let computer run, like for example, run 100 times. So each time computer select the duration of this activity based on if you have done 100 times, you just pick up any random point of that. It can be 31 days, can be 32 days, can be 40 days. So every time you pick up different date for different activities. So each time you run, your end result may be like 10 months, 9 months, 8 months. And each time, if you run 100 times, you have 100 time different total project durations. And once you have that, you will be able to look at distributions and see, okay, what is most likely, how many days will take, what will be likely if we have 10% risk of exceeding, how much will be, like for example, if there's a huge penalties of late completion, you want to know what will be a probability my project will be delayed. So that you want to make sure that you take that risk into your equation. So basically that will be the decision making. And also actually this is a lot of engineers ask me, if you are new to the US engineering market, you want to know actually who makes the decisions on bridges. So we found this is the decision making, this is a chief engineer of transportation department, and that's a consultant, and that's an engineer, basically just the project manager at the department, and that's other people. So basically most decision is made by the engineer who manages, in other words, who works for the government, who manages the project. And that's his boss. So their decision is more than 50%. And the consultant actually, although consultant make decisions, but he has actually only 30% influence on a particular project. And that's actually also, actually that's another statistic about the factors. We talk about decision making. What factors is typically considered and how important they are? Typically, the durability and the maintenance is a very important elements. And I did not put the construction cost. Construction cost is much larger, so that's always the most important. The outside the initial construction cost is that also, although low initial construction cost is part of this equation, but usually it's most important elements. And what kind of material people use, reinforced concrete, steel, pre-stressed concrete, and so on. These are trends, and the percentage. We found that more and more people using pre-stressed concrete. This is relatively cheaper and easy to build, and they have less maintenance. So this is a preferred option for small, short span to medium span bridges. And basically, these are the trends of different structures based on based on type of structures. Like if you have curved bridge, and then you have different ratios of each materials. And if you have very, very simple ones, you may have different ratios. And so, again, the span length play an important roles for different type of material you use. In general, the longer the span, the more likely people choose steel because it's lighter and easy to fabricate or easy to erect. The shorter you use pre-stress concrete. And if it's really, really short, you may just use regular concrete. And the preference is different at locations. Different locations, because they have different climates, they may use it. They may have different preference. And again, I think that is a very, very similar as for like a curved material for the curve. Once you have curved structure, steel become a lot easier because steel fabrication of any shape is much easier, and also steel box has much better like a rigidity against torsion. So that gives a conclusion of decision making. Decision making again is very, very complex, and I spent about 3 years to study decision makings, and I'm sure I'm still very, very. I only know probably very, very small portion of decision making. It's just too much. But I found like once you study computer simulation, that can be used for very much everything. Just like before, my professor told me like it takes long time to study like a structural behavior for solid or shear type of elements. To develop mathematical equations, it's almost typically they use like energy method, try to develop different equations, and the equation becomes so complex, not even math professor can understand. But later, people develop a new method called finite element analysis, which means anything I can calculate. Although I may not be able to develop a model for it, but I can tell what result is. Basically, I just use a computer to get approximate answer for me, and that's good enough. That's why now not a lot of professors are studying what kind of mathematical models will be for the different kind of structures, because it's very much covered by finite element analysis. Decision model is the same. Once you have computer simulation, you can easily do things. And probably, if you have that question, we can discuss further. And now it's 3 o'clock, we can have a break.